Welcome, everyone. Thank you for joining us for today's webinar. My name is John Bond, and I'm accountable for the sales and marketing at medmont. For over 20 years, medmont has been one of the leading providers in the specialty care eye space. We at medmont are extremely excited to share with you today our second webinar of 3, introducing our new advanced topographer, medmont meridia. Today's session, titled as the new medmont meridia advanced topographer, New Imaging Benefits for Specialty Lens Practitioners, will be presented by Randy Kojima. Randy is the Clinical Research and Development Director for Precision Technology, based in Vancouver, Canada. He also serves as a research scientist and clinical instructor at Pacific University College of Optometry in Forest Grove, Oregon. Additionally, he is our clinical advisor at medmont. Randy has published numerous articles and submitted posters on various contact lens related topics, as well as been a contributing author in several textbook chapters. He lectures globally and has a passion of sharing his insights, methods, and research with eye care colleagues from around the world. Randy is a fellow American Academy of Optometry, the British Contact Lens Association, the Sclera Lens Education Society, and the International Academy of Ortho-K. At this time, I'd like to welcome Randy. Thank you, Randy.
Hey, John, thanks very much. And thanks to medmont for giving me this opportunity to share some of my experience with medmont meridia. We've had one for about a year now, and we just love using it for everything related to specialty contact lenses. Now, of course, for those of you involved in dry eye, you're really going to enjoy Steph's lecture coming up next week. She's really going to focus in on those features that make this tool such a broad, incredible piece in your practice for so much more than just topography or just contact lenses. We're able to do quite a wide range of things with it. But today's talk today is really going to focus very much on the contact lens application, and we'll try to do that through various cases that recently popped up, and see if there's anything that we can learn from each one. So let's get started. And here's our first patient. What is there to learn from a very simple, very uninteresting spherical cornea? Well, let's talk about what we can take from the software that's useful to us related to any contact lens that we might fit. Well, let's first start with what we see. And looking at the color contours, what is it that you notice in this eye without seeing any of the metrics like the K readings or any shape data? What do you notice when you look at this topography? And one of the first things that I'm always interested in is the peripheral shape of the eye, especially related to a specialty contact lens, like a rigid contact lens. Where will a lens center based on where it lands in that far periphery of the cornea? So what we might do is highlight that green-yellow border. That's the approximate area where a large diameter GP lens would land, a corneal GP. And what you might notice is that white dotted circle is really well centered to the pupil and the center of the topography, telling us that if we were to place a rigid contact lens on this patient, chances are it's going to center really well. So that's kind of a helpful understanding, because if we see a highly displaced corneal cap that might suggest the lens won't center well, we won't be surprised if we go down the orthokeratology path and that lens wants to decenter. But here we see a very symmetric, well-centered eye. Now, what about the colors that we see distributed across this eye? One of the first things that you might do, at least what I'd suggest to do, is use what's called a normalized scale. And what that does is it distributes all of the colors that you can see across this particular eye and its related radii. So for this particular patient, the most blue, or the flattest we can read, is about 35 diopters. The steepest we can read is about 44 diopters. So that's a 9 diopter distribution of power. Very normal. When we're looking at diseased eyes, it's nice to look at something very quickly to tell us, are we on the border between abnormal and diseased? Is this a patient that we should think about cross-linking as an example? So that scale range can be helpful. Another thing that obviously stands out to us is just looking at the center contours and how we're really not distributing much power within the pupil or across the center 5-6 millimeters of the cornea. It's primarily two colors. It's about a half diopter separated. So imagine correcting this patient with spherocylinder refraction. This is going to be a patient you would expect should refract to a very high level of visual acuity because the central cornea is so normal in power distribution and simple. Now, of course, K readings are that value that we always want to default to. It gives us such great perspective on the corneal astigmatism of the eye. Clearly, this is a very uninteresting spherical cornea, median radii of 4350, so nothing crazy interesting there. But when we go to the eccentricity of the eye, it gets kind of more interesting on this case. We have a flat E of 0.65, meaning the cornea has a normal rate of flattening from center to periphery. Now, so what? Why do we care about the eccentricity of the eye? If we're thinking about corneal GP lenses, the higher the eccentricity is, the more the cornea flattens. So in corneal GP worlds, you would be thinking, I'm probably going to need a flatter peripheral curve system if my E value is much higher than the norm of about 0.65. Conversely, if you had an E value of, let's say, 0.45, much lower than the average, then you know the cornea has a lower rate of flattening, and therefore you may need a steeper peripheral curve system with your rigid contact lenses. And Ortho-K is another good example where maybe we need higher edge lift or lower edge lift based on whether the E value is median, high, or low. Now, related to Ortho-K, another thing that we can consider in eccentricity is we find that corneas that are higher E value tend to respond better in orthokeratology. Eyes that are lower in E value tend to respond poor in Ortho-K. So if you're trying to get an 8 diopter effect out of a eccentricity of eye that's 0.3, probably not going to happen. If you're dealing with a high eccentricity eye like 0.7, 0.8, and you need an 8 diopter effect, then you got a much better chance of being able to achieve success. Now, when you compare the flat and steep E, you'll notice 0.65 versus 0.53. They are very similar rate of flattenings between the two principal meridians. And that tells you that around the peripheral cornea, there's not a huge difference in height. And therefore, a symmetric, maybe spherical landing is more likely to work for this eye. In other words, we probably don't need a toric or asymmetric landing. Now, another thing that we can look at are the disease detection indices. And obviously in this eye, nothing interesting to learn here, but when you see the disease detection indices light up in green, you know it's normal. When medmont tells you they're yellow, they're suspect, they're nearing that threshold of abnormal. If you see them yellow, then you know that that's a patient over the threshold of abnormal and one that we should be looking at following in a more significant way, especially if it's a young patient and we're thinking about the possibility of cross-linking. What else could we look at? The pupil width is a helpful number. What if this is a patient that we want to fit with multifocal contact lenses? If we have a pupil size this big and an add power that kicks in at 4 millimeters, how are we ever going to provide this patient with the multifocality? If we're fitting this patient with orthokeratology and we have a 2.7 millimeter pupil and we need the aberrations and the defocus to kick in at around 4 millimeters, 5 millimeters, 6 millimeters, then we're not going to get the patient into that aberration or defocus that we need to slow down eye growth. So here, pupil size can be helpful to give us some guidance, especially when we're dealing with any kind of multifocality. Now, the sagittal differential is one of those numbers that whenever I'm using rigid contact lenses, I'm really interested in what that is. And because it tells us when do we need toric and when do we need a symmetric landing. And the threshold is about 30 microns. So whenever you see your sagittal differential at 8 millimeters, when it's 30 microns or greater, you're thinking about a toric rigid contact lens, whether it's corneal GP, single vision, multifocal, or orthokeratology. Now, another thing that the medmont does that's really helpful related to specialty contact lenses is the estimated height attribute. And what this does is it's taken research that our team at Pacific University has done to understand the peripheral corneal shape. We can take the depth of the cornea and the peripheral the angle of the eye to predict the anterior chamber depth for scleral lenses. So in this case, I have the estimated height chord set at 15 millimeters. You can see that right here. And that is because the scleral lens I use is a 16.5 diameter lens that lands at 15 millimeters diameter. Its sagittal depth is determined at that 15 millimeter diameter. So if I want to choose the initial scleral lens based on the appropriate sagittal depth, then I set the chord here for the diameter of my scleral lens height measurement, and then the software will calculate for me across the 0-180 meridian, the 150, 330, and the 3210 meridian, the height that it's coming up with. And you notice that it's estimating the sagittal depth of the anterior segment across 0-180 is about 3,650 microns. The highest number across the 30-10 meridian, about 3,750 microns. So somewhere around a 3,700 micron height is this cornea, and that you would add your fluid layer, and that would tell you the sagittal depth of scleral lens that you should pull out of the set. So for any of you that are scleral lens users, this can be a helpful starting point. Obviously, K readings in a scleral lens are pretty much useless, so understanding the depth of the eye gives us a much better starting point in any of those large diameter lenses. Now, finally, some of the other data that I like to have up on the window is the aberrations. And this is related to any work we do in myopia control, especially related to ortho-K. Research tells us that the more we increase spherical aberration, the more we increase coma, the better the myopia control. Now, this is a pre-fitting corneal shape, so these numbers are only helpful when compared with the post-ortho-K values, but by having both of these numbers up when we compare pre versus post-ortho-K, we can get a sense of how good a job are we predicting that we're going to do for myopia control. Now here's our second case, and in this patient, obviously a little more interesting, an astigmatic eye. Now what can we learn about a simple, regular, with the rule astigmatism? Well, first, let's talk about the coverage. If we're going to fit a corneal GP lens on this patient, then we want a fair amount of corneal coverage. And one of the benefits of the medmont, of course, is that we get this large surface area of capture. And that's approximately, on this eye, 11.25 millimeters. So one of the benefits of using a small cone instrument is that its focal distance is short. So it's able to bring the cone very close to the eye and push the rings to the peripheral cornea. We get a large area of information on eye shape, eye power, and elevation. The medmont composite eye is a unique feature that the medmont topographer introduced a number of years ago that allows us to change fixation, push the ring data to the periphery of the peripheral cornea all the way around. Those photography images are converted to a colorized topography, and then a very complex algorithm will merge all of those images together to create a larger view of the eye. And so that gives us this very complete view of the cornea, generally limbus to limbus. Now imagine, related to scleral lens fitting, if you're trying to predict the peripheral corneal angle and how that angle runs through the limbus and into the sclera and can help us to predict the initial scleral lens depth, then having a composite map is highly valuable because it's going to do a better job of predicting this angle that forms in the peripheral cornea that tends to run into the limbus, well into the sclera, and it gives us a very good idea of the depth of scleral lens that we need. So a very helpful capture option. Now that's scleral for a huge lens, but think about it just for corneal GPs. What's your normal corneal GP diameter today? You know, how many of us are still using 9.2 or 9.5 diameter lenses? Today's corneal GP is 10.5 is a median diameter of lens. In orthokeratology, they're typically more like 10.6 to 11 millimeters. So having this large area of information gives us better prediction of the initial lens parameters. And in my opinion, the reason to get a medmont related to specialty contact lenses is to have that information so that we have very accurate initial calculations of our specialty lenses. Cut down on chair time, improve the first fit response, improve the patient experience in your practice. Now, the single map capture does give us a very large area of information. It's very useful regardless. We get almost the entire cornea with that one single image. But if we're building a large diameter lens, it is helpful to get that composite eye capture. Now, when would you do one or the other? If you're doing a simple screening, if you want to understand the orientation of the astigmatism, is it regular, is it irregular, is it a diseased eye, what kind of post-surgical condition are you dealing with? If there's any basic understanding that you want of eye shape, power, or elevation, you can just use the single map capture. If you're wanting to build a specialty contact lens, a large diameter lens, a rigid contact lens, then you're going to use the composite map. It's really going to give you so much data so that you can build a more accurate initial lens. Now let's go back to this astigmatic eye. What can we learn from this cornea? Well, it's a slightly more astigmatic eye than we might call the norm. We have 2.86 diopters of corneal astigmatism. So certainly a patient we would expect to use a toric rigid lens. What else can we learn from this eye? Well, let's look at the sagittal differential. That was that number we talked about earlier. What this does is it looks at the height of the eye, not the radius of the eye, not the power of the cornea, but what is the height of the eye like a mountain? On the flat, then the steep, and the difference between those two sagittal depths will be the sagittal differential. This patient has a 78 micron difference between the height of the eye on the flat and the height of the eye on the steep. Now, remember earlier we talked about the threshold of using a toric rigid lens is 30 microns, and this patient has a 78 micron differential between the height of the flat and the height of the steep. So clearly, this is a patient that needs a toric corneal GP lens or a toric ortho-K lens. And that certainly makes sense, doesn't it, with the high corneal astigmatism of almost 3 diopters. Well, let's use the contact lens software. And this is a function that we use all the time at the school. The benefit of this is it allows us to place a rigid contact lens on eye and model its fit, manipulate its parameters, create the best possible lens to cornea relationship before we either order a lens and wait for it to come in or put a diagnostic lens on eye and find out that we're either too steep or too flat. So the contact lens software allows us to place a lens on the eye in a theoretical environment. Now here is our symmetric spherical 10.5 millimeter lens on our pretty toric cornea. And let's assess the success of the appearance of this pattern. Now first, you might look at the apical clearance right in the center. We have about 20 microns of fluid under the center. So this is good. This is the appropriate fluid under a rigid contact lens so that you and I can just make out the fluorescein between lens and cornea. The second thing we want to see is we want to observe along the flat meridian of the eye how the lens lands down, hopefully at 3 and 9 o'clock, as we see here. At 3 o'clock, you see your touchdown point. At 9 o'clock, your touchdown or alignment. So this is good. The lens will the lens will land far out in the periphery of the cornea. It should be laterally stable because you've placed that bearing far out on the cornea. Then secondly, because it's along the horizontal meridian, the lens shouldn't move laterally, and with the blink and gravity, it should be moving up and down, creating good tear exchange. Now here is the steep axis, and on our very toric cornea, you notice the challenge of fitting a spherical lens on this very toric eye. We're going to have boatloads of fluid underneath 12 and 6 o'clock. So our contact lens is most likely going to be just rocking back and forth across that steep meridian. So what lens do we need to best serve this patient's interest in rigid contact lenses? And of course, a toric lens. So let's place a bitoric lens on eye in the software. Across the flat meridian, let's maintain that same relationship. About 20 microns of apical clearance, landing at 9 o'clock, landing at 3 o'clock. So across this meridian, you're looking at the tear layer profile underneath that contact lens. Now, when we switch to the steep axis and using a toric lens that has a much steeper, a much deeper vertical meridian, we now create a lens that has a relationship that's more even all the way across. Notice 20 microns at the optic zone junction here, and a little under 20 microns at the optic zone junction here. So now our contact lens doesn't have all that fluid and all that depth that it can rock back and forth against the cornea. We should create a more stable fit. And here's the lens that we ordered and placed on eye based on the medmont contact lens software. And this is the medmont meridia imaging using the cobalt light in the software. And this allows us to now use the instrument like a slit lamp, but also as a tool to take an image or to take a video that we can document the fit or that we can share with the lab if we feel that modifications are necessary. One thing that you'll notice is that the way the meridia illuminates its both white light, the cobalt, and the bibography is you get this really beautiful illumination across the entire field. So you don't have that slit lamp-like one single source or angle of light illumination. You really get a beautiful illumination across the entire field. So it's really an exceptional imaging device. And like I say, a really good topographer. It just also does really good imaging as well. Now, one of the benefits that I think is maybe most significant to practitioners who aren't very experienced with building specialty contact lenses, it's kind of nice to collect the information and be able to share it digitally with the lab so that they can construct the appropriate lens from that information. Or in this case, if we've had a starting point in the lens, now I can send the topography and the fluorescein video or images to the lab. I just highlight the data I want to send. It creates that one single export file you see here, and then we email it off to our lab consultant and they can assist. Now imagine trying to share a PDF of your values, of your images or your outcomes. Of course, that two-dimensional copy really doesn't give much in understanding what's happening with the topography, what's happening with the floor scene. You know, being able to send a live video, being able to send the digital topography so that the lab consultant can upload it to their medmont software and build the cornea in 3D space, and also use the contact lens software the way you did and see if there's any manipulation that can improve the outcome. So being able to digitally share these medmont export files is a really valuable function. Let's take another case. Here we've got another pair of astigmatic eyes, and we notice that that hot meridian appears to run from one side of the eye to the other. So while this is a with the rule astigmatism, it's also a limbus to limbus astigmatism. Now, what does that mean relative to us fitting a specialty contact lens on this patient? Well, let's look at that. Now, the first question you might ask looking at these topographies, is this patient a good candidate for orthokeratology? Is every patient a good candidate for ortho-K, or are there indicators that will tell us when we have a good from bad candidate? Excuse me. Now, certainly K readings do provide some indication. We talked earlier about the radius of the cornea. The steeper the cornea, the better the potential for ortho-K. So if we're dealing with a steep radius of flat K or central corneal radii, that might be suggestive that this is a good patient for ortho-K. If we had a 40 diopter cornea and a -6 RX, it might be tougher to get that 6 diopters of refractive change. So here we see a pretty median cornea, 43/50 on the one eye, 43 on the other. We look at the astigmatism, 1.5 diopters on the right and 2.5 on the left. Certainly the right eye is within a very predictive and easy range. Left eye is certainly doable, but you know that it will be slightly tougher as a higher astigmatism in ortho-K. Remember, we talked about eccentricity. That is the rate of corneal flattening from the center of the eye to the periphery. The higher that change, the better the potential for ortho-K. On the right eye, this patient has a 0.66 E-value, very normal. So again, a good candidacy for ortho-K. On the steep meridian, you'll notice a bigger differential between the flat and the steep. 0.66 on the flat, on the steep, 0.35. When those two meridians have very different E-values, then you know that your peripheral cornea has more toricity, or more likely to need a toric landing. Now also consider, if you need 8 diopters of flattening on the flat, and you need a 2 diopter astigmatism to be corrected as well, you need your 8 diopters on the flat, you need your 10 diopters on the steep. You need a lot of eccentricity to be able to move that that vertical steep meridian out of the way. So if we don't have a high E-value on the flat and steep, then consider what that means to your potential to move out both the sphere but also the sill. Let's look at the left eye. We have 0.66 eccentricity on the flat, 0.3 on the steep. A big differential between the two. That might suggest two things: that one, we may need a toric lens, and two, that we may have a tougher time pushing the astigmatism out of the way with the lower E-value in that meridian. What about pupil? We talked previously that if we're doing orthokeratology on a myopia control case, we want to try to push the aberrations toward the periphery within the pupil. We want to try to push more plus power into the eye, more defocus, to slow down eye growth. And with this pencil of a pupil that we have, it's going to be very hard to create good myopia control. But conversely, if this were an adult and we were wanting to provide orthokeratology to free this 40-year-old soft lens wearer that was having dry eye issues with their lenses, free them up of contact lenses, provide them with ortho-K where they're not wearing a contact lens in their air-conditioned environment during the day, in their eye that's beginning to dry out more and more over the years, then this would be a very good candidate with a small pupil. We're going to have very low aberrations. Our patient is probably going to be very happy in orthokeratology. Now, let's look at whether the eye requires a toric lens. And we talked a little bit about the difference between the eccentricity in flat and steep. Let's look at the sagittal differential. What is the height of the flat? What is the height of the steep? So thinking of those two eyes in elevation, what is the difference between the two? And on the right eye, we have a 33 micron differential. So we said that 30 or greater, that's when you would consider a toric. So on this moderate corneal astigmatism, remember it's 1.5 diopters or under 1.5 diopters, this patient would require a toric lens or would likely do better in a toric lens than a symmetric landing. How about the left eye? We'll measure the flat, measure the steep. What is the difference? And we see 63 microns of sagittal differential. So I need this value from my medmont before I start any rigid contact lens, and especially ortho-K where centration is paramount. It's nice to know before we start, are we leaning towards spherical landing? Are we leaning toward toric? Are we somewhere in between? And in which case, I might just choose the toric anyway. So basically, on pre-fitting orthokeratology, everything you need is within that window. All the information is there for you to get an idea of, is this a good or bad candidate for ortho-K? Now that's the metrics. What if we look at the topography itself? When you look at this map, does this tell you that this is a good patient for ortho-K or not? And I want you to look at the corneal displacement. Look at how the contours change from center to periphery. Imagine where a rigid contact lens is going to find its alignment on the peripheral cornea. And is that peripheral cornea centered to the pupil or the visual axis? So let's draw a couple circles around that green-yellow border that we see in the periphery. And you will notice in both eyes, we have a fairly displaced corneal cap, let's call it, in relationship to the pupil and the visual axis. So that tells us before we start that centration for this patient may be a challenge. When that lens goes on eye and it finds its equilibrium, because we have a slightly displaced cornea, that lens will similarly follow that displacement. Now this is an axial map. We could also use the tangential map to see that same displacement. But the elevation map does tell a very key story here. You know that red is where the elevation of the eye is very high. A rigid contact lens is not going to move in the direction of the greatest elevation where there's going to be that resistance. It's going to move where the elevation is the lowest, toward the lowest point on the cornea, where it has the least resistance. So when we look at these two eyes, in terms of the elevation map, one would expect our contact lenses to want to ride temporal, away from the red, and ride inferior toward the lowest point of elevation on the eye. So I don't think, looking at both the axial and the elevation map, that we're going to have perfectly centered bullseyes. And that's helpful to know before we start, because we won't be trying to modify the lens or creating multiple visits to the office trying to improve the centration when really the lens has found its equilibrium on this eye, and we're not going to be able to change what's there. Now, a question, as we begin to start ortho-K, how do we build a lens for this patient? What would be the method that you would use to construct an ortho-K lens? Well, let's use something called the ideal eye. And this is where medmont converts the topography into a symmetric surface between the two principal meridians. Now, the reason why you might do this is it does a very good job of predicting the fluorescein pattern of your ortho-K lenses. I don't use the ideal eye on conventional GPs. They're less sensitive to microns. We can miss in a corneal GP by a lot more than we can in an ortho-K lens. For instance, we talked about how a corneal GP, we would desire to have about 20 microns of fluid under the center. In an ortho-K lens, how much fluid do you target in any rigid, any reverse geometry ortho-K lens? And that's typically around 7 microns of fluid under the center. So we don't want to miss by too much, or we risk the contact lens coming into touch with the eye. So I use this ideal eye because what it does is it smooths over the horizontal and vertical meridian, or the flat and steep meridian, and it will give me a very good idea, if my ortho-K lens decenters even a little bit, what the fluorescein pattern might look like. So then, once I've got my ideal eye, I'm going to select the lens that we're going to use. In this case, we might use the B-free lens. I'll enter in the RX, and the software will calculate for me the appropriate starting point. Now, I have the ability to select a symmetric or a toric lens. In this case, the default is a symmetric. And what can we learn about the fitting of this theoretical pattern? Well, let's start with the flat meridian of the eye. And here we see across this blue axis, the flat meridian, we've got our lens that lands down at 9 o'clock. It lands down at 3 o'clock. It's looking good. We've got good edge lift on both sides. And then you have your reservoir that runs all the way concentrically around the lens. And then, of course, the apical clearance of around 5 to 10 microns, roughly. Hey, this is looking good, right? We've got a good ortho-K starting point. Lens is landing at 3 and 9 o'clock. We've got good, healthy edge lift on both sides. We've got that reservoir to change the peripheral corneal shape, and we've got that base curve that comes close to the corneal surface without touching. So this is an ideal ortho-K lens. Well, let's go to the steep meridian, and you'll notice along the vertical, in this case steep axis, your alignment zone is hanging over 40 to 90 microns above the eye surface. So where we want our contact lens to be near to in alignment, that lens is hanging so far off the cornea that a centered fit, a lens that's stable, is unlikely. A lens that's comfortable is unlikely. And a lens that will produce the hydraulic force is also not expected from this kind of relationship. What do we need to do? And of course, we need to build a toric lens. So on the flat meridian, we want that same relationship. Whatever the parameters of lens are across this meridian, I want to preserve that. Whereas on the steep meridian, I want to completely alter the reverse curve of the lens. I want to completely alter the alignment zone and the periphery of the lens to create an appropriate vertical meridian relationship. Now, how hard was it for me to do this? Did I need a bunch of expertise in the medmont software? And basically, this is how simple it was. I selected the lens design I wanted to use. Then I selected that I wanted a toric landing because the sagittal differential was 33 microns. It's over the 30 micron threshold. I know I need a toric. And then I let it calculate the lens, and we're done. We have an appropriate relationship built 360 degrees around for this eye. So this is how you'd use the contact lens software to build your ortho-K lens. Or if you don't want to use the contact lens software, if you want to use the accuracy of the medmont topography and let your lab just build the entire lens, then you create that digital export file, send all of that information off to the lab. They can reconstruct the eye in 3D. They can drop the lens on the cornea using their software and determine the appropriate parameters of lens. So a very efficient way of building a ultra specialty contact lens like a reverse geometry ortho-K lens. Well, here's the lens that was built from that theoretical pattern. Notice you get that typical toric ortho-K pattern where it looks thinner in the reservoir across the flat. It looks wider or deeper across the steep. We have a lens that has beautiful alignment all the way around, a healthy edge lift, and a lens that we would predict will perform well in the closed eye environment. And again, this is your medmont meridia taking its cobalt photography of our lens. So using the topographer, we have an ability to understand the corneal shape, the candidacy. We can build a lens, we can order that lens, and we can then take do our assessment and take images and video from the same instrument. Now, once we've done the overnight, we need to assess the post-treatment outcome. And how did we do? And I picked for you the tougher left eye that has the 2.5 diopters of corneal astigmatism, the limbus to limbus corneal sill, the high horizontal E value, the lower vertical E value. Let's see what happened with the fit. Now, one of the first things you might look at is you can click your cursor in the center and you can see the refractive change that was created. 1.25 diopters after this one night of treatment. So if we were hoping for 3 diopters of effect as an example, we wouldn't be surprised that we're under-correcting after one night of ortho-K. We obviously know we need a week for full effect. What else can we learn? We could look at the position of the blue treatment zone in relationship to the pupil. So the axial tells us the refractive change, it tells us the treatment zone position, it tells us the treatment zone size. And we'll talk in a second about how it can tell us something about the myopia controlling effect. Well, it's looking like our lens is riding down and out on this left eye. Now, is that as good as it's going to get? And we said, looking at the baseline topography, that the contours are all pulled temporal inferior. The elevation map told us that we had an incredibly high point on the nasal side and incredibly low point on the temporal side, driving that lens down and out. So this is likely as good as it gets for this patient. If this person were 20 happy, I would not worry about the fact that this is really a inferior temporal displacement of this outcome. I'm thinking this is as good as it gets. Now, could we try to modify it? Of course. We could flatten the alignment zone to bring the lens up to create less of what you see as a frowny face topographical outcome. If we thought the lens wasn't laterally centering well, we could fit a larger diameter or fit a tighter alignment zone to see if we can bring it more onto lateral center. But if we try that and it doesn't change the fit or sends the fit in the wrong direction, you know that this was as good as it gets. Now I just want to focus in for a second. Here's your pupil. Right in the center of your pupil is your visual axis, your focal point for the patient. Now look at the blue treatment zone, that yellow dotted line. Notice how decentered it is in relationship with the pupil. Then you get a really good idea from this, the axial map, where your treatment zone is in relationship to what you like as the visual axis or the pupil centration. So axial is for visual cues. The tangential tells you where the lens was in the closed eye environment. And we do that by, again, looking at where the pupil is in relationship to this red ring. This yellow is defining where the red ring of the paracentral steepening is on the epithelium. And that's created by the reservoir, the suction force of the lens. That creates this ridge that you see here. Now there's another ring that we can look at in ortho-K post-treatment, and that's the blue ring. This is where the lens touches down on the eye surface, creates its alignment with the peripheral cornea. So we can tell by the red ring and the blue on the tangential map where our contact lens is centering in the closed eye environment. And again, riding down and out, most likely because the corneal cap is displaced down and out, and the elevation map is telling you that it's going to resist going nasal, and its path of least resistance is inferior. So inferior temporal is probably where it's going to go. Now we could look at the astigmatism pre-treatment and post-treatment, and you see this 2.5 diopter pre-treatment corneal cylinder was not pushed out of the way post-treatment. We have 1.84 diopters of corneal cyl. Now this was only one night. We need more days of effect to see what happens here. But if we don't push this astigmatism out of the way, we won't be surprised. The baseline cornea showed limbus to limbus corneal astigmatism. The baseline cornea showed us a much lower E value in the vertical meridian. Both those things together telling us that this is a slightly more challenging case. So we may not be able to push that cylinder out of the way. But again, I keep going back to this, forgive me for beating a dead horse, but this is where being able to send the digital files, your pre-treatment, your post-treatment, your fluorescein pattern, digitally to the lab, and they can assist. What do they feel is the best way to approach trying to squeeze out more effect? Is it to use a flatter base curve to cornea relationship, more suction force, more hydraulic force? Is it to alter the landing of the lens to change centration or to change how it traps that hydraulic force in? Changing the optic zone size. What are the ways that the lab feels is the best approach to try to modify this outcome? I can tell you that this patient did very well in Ortho-K. Although it was an inferior temporal displacement, this patient was happy with the outcome. It was one lens to achieve success in both eyes, even on that higher astigmatism on the left eye. Now, just for a second, while we're talking about Ortho-K, let's make sure we talk a little bit about myopia control. And when we're looking at our post-treatment outcomes, we want to make sure that we are sending this patient off with this Ortho-K lens for the next 6 months or a year, knowing that we're doing a pretty good job of both Ortho-K and myopia control. Now, as an orthokeratologist, I'm happy that my blue treatment zone on the axial map is centered. That will provide the patient with likely good quality of acuity, good AM to PM vision. Now, is this good myopia control? And what you might look at is here in the center, the most minus is down here on the graph. That's where we create our foveal correction. And we want that change to be equivalent or slightly higher than the refractive change. So in this case, we have a 3.09 diopter RX change very close to the center, and that's creating a appropriate refractive change for this patient if we're a 3 diopter myope. However, when you look at the periphery, as we move away from center, you notice that that effect is lost very quickly, and we're going down to a much lower power as we reach this dark gray area. That's the pupil. This dark gray is the pupil that medmont is defining. So if I look at the most minus, about 3 diopters, the most or least minus, the most plus, at the border of the pupil, that's approximately plano. So I have a 3 diopter add being created between the most minus and the most plus. So when you're looking at your medmont topographies and you're looking at that post-treatment analysis, don't forget to look down here at the graph, and that will give you some perspective on whether you're creating a strong plus signal, a strong myopia controlling signal, effectively an add power for the patient. Whether you're creating a high spherical aberration and you're ramping up that spherical aberration that's been shown to slow down eye growth. Another way that you could look at it is if this is a little bit confusing, you might find looking at the numeric meridian map as another way in your medmont you can assess the myopia controlling effect. Now I'll blow that up and you might look at this value right in the center, 3.2 diopters, heading toward the temporal side, we see that it's 0.1 diopters effect, going north about 0.1 diopter effect. So essentially you have a 3 diopter add from minus 3.2 down to basically plano. We're creating this huge add power from center to periphery. Not the same value heading toward the, sorry, this is the temporal side here. We've got maybe 1 diopters effect. So going from minus 3.2 down to minus 1 is a 2.25 add. Now, if we think about this related to soft lenses, what's a soft multifocal lens supposed to do in myopia control? It's supposed to create a high add for the patient. Now, even in the meridian of least effect, our ortho-K lens is producing a 2.25 add in this direction. It's producing almost a 3.25 add in this direction and this direction. But you get the idea. You can use the axial analysis to get an idea of, are we heading off in the right direction of myopia control for this patient? So that gives you some idea of how we might use the meridia in specialty contact lens practice. I would have liked to have a little more time to talk about how we use it in scleral lenses, but we can reserve that for another talk. Hopefully that section will have provided you with some idea of how we use it related to corneal GP lenses. So just as a reminder, use that single map capture to get any type of screening topography. The medmont small cone topographer gives you that huge area of information. And again, in my opinion, is that the reason to have a small cone topographer is we get that large area of information. The medmont is super accurate, which helps in any kind of specialty contact lenses built with microns of accuracy. And in the case of any large diameter rigid lens like an ortho-K that might be 11 millimeters or a scleral lens that might be beyond 11 millimeters, I like that composite capture because then I get all that peripheral information that gives us a more accurate starting point. And of course, being able to place one lens on eye, one diagnostic or one custom lens, and be one and done makes us much more efficient. It's a better experience for the patient, more profitable for the practice, so lots of reasons to do that. Now, as far as the photography is concerned, the white light imaging, as you can see in this image, gives us this really beautiful illumination of the entire field. And then another thing that you get from your medmont meridia is this wonderful depth of field as well. So the camera and the system that medmont has used to build this instrument for imaging either cobalt or white light is really awesome. I had one practitioner from a university say to me that I just spent $50,000 on a wicked good slit lamp camera system, and I could have got a meridia instead, and I would have a corneal topographer and a great imaging device. Because of that illumination, you're able to also take images of both the lid margin, the lashes. You really get awesome imagery, not just of the cornea. And the white light photography is great for all of your contact lenses, soft included. In this case, we have a scleral lens with a bubble underneath it, and we notice those markers used to determine whether we have the right diameter. And because the markers are falling within the visible iris in some places, I can email this image off to the lab and ask them to resize this lens appropriate for this particular eye. Then, of course, in the fluorescein analysis and video, then we've got a tool that we can both document, we can analyze, and we can share with the lab. So a really great tool. Again, notice the illumination across the entire field. It's really not this one axis that you get good illumination, and there isn't any shadowing that we often see, especially in our scleral lenses. So the meridia does a really great job. In your ortho-K lenses, we probably need this kind of imaging the most, where we're trying to create those finite little changes to create the perfect outcome. being able to, again, share this with the lab is a valuable tool. Now, the meridia is not just a topographer using those Placido rings. We can do some things related to dry eye analysis. We can analyze the surface fluid rather than the eye shape. And that gives us the ability to do non-invasive tear film breakup time testing and to understand the entire, or virtually the entire cornea and the surface quality of that reflection. So this topography tool that also does imaging is also a dry eye tool. And I know Stephanie Wu is going to go over that in next week's session, so I won't spend a great deal of time on it. You can also do tear meniscus height imaging, which again is helpful when you're building your dry eye analysis for this eye. Mybography, another imaging option that the meridia provides using that infrared light. And again, we get this wonderful imaging across the entire surface of the meibomian glands. Then, if we take all of that imaging together and put it together with grading scales, there's the option within the medmont meridia to assess your grading scales based on the Efron scale or the Brian Holden Vision Institute scale. So you've got some flexibility within the software itself in building your dry eye report. So you would select all of the images that you want to use to compile in your report. That can be done super easily with the thumbnails. Then you enter in the data that you feel that you're dealing with. Is my tear film breakup time X amount of seconds? I enter it in here. The software will tell us yellow being somewhere in between suspect of dry eye, red obviously being where we're over the threshold or feel that this is a very strong indicator of dry eye, and green where we have normal values. That data that we use to build the dry eye report can be used to, is used to print out and provide the patient with an understanding of the entire assessment of their dry eye disease and the reasons and the rationale for the treatment that you're recommending for this patient. So a really valuable tool as a whole. And I'm excited for Stephanie's talk next week to learn how she uses it in her both dry eye and specialty contact lens practice. Now finally, field of view, you'll notice for both the topography, the white light, the fluorescein, the mybography is really an awesome diameter. And then of course we have this high res image that we can zoom in and zoom out of to assess areas that we really want to focus in on. So a really impressive camera that's being used in this instrument. So you really have this incredible tool in the medmont meridia where you have possibly the best corneal topographer, certainly based on the comparison of the E300 versus the meridia. The data is the same, and we know the E300 was a really awesomely accurate instrument. So for building of your specialty contact lenses, this should be the most accurate and efficient tool that we could possibly use to build lenses. We've got a tool that does dry eye assessment. We've got a tool that images our fluorescein of lenses or of the eye, the naked eye by itself. Is there staining on the ocular surface? Is there staining on the conj? So, wow, what a tool this is, and we just love our medmont meridia at the school and at the research center. Hey, so thank you everybody for logging in to be with us. I hope that this session has had value. I'm going to pass this off to John to explain to us what's coming up in the next session with Stephanie Wu. So again, thank you everybody. John?
Thank you, Randy. This completes our second webinar out of a series of 3. And as Randy has indicated, Stephanie Wu will be with us next week. I'd just like to thank you, Randy, and thank you, audience, for your time and attention tonight.